Have you ever taken that photograph which, disappointingly, is ruined because something or someone is moving across it so fast as to leave a blur? I know I have. Frustrating, isn't it? Given that a dog moving relatively slowly can ruin your artwork, how would you take pictures of something that's moving super fast? And I do mean really super fast, say like an electron, as it spends its time in the cloud around an atom. Recently, 3 physicists have been awarded the Nobel Prize for their work in developing practical techniques which should enable us to do exactly this. And when you strip down all the really complicated physics, the underlying principles are actually not beyond your average 6th form or higher level physics student at school. Using commonplace kit like mobile phones, it's easy to get an idea of how, say, a bird flaps its wings just by filming it at 30 frames a second. But if you want to get super accurate about the velocities and positions of, say, bits of that wing at particular times, you'll need to take pictures much faster than this. 30 frames a second just leaves things blurry. Although you may not have thought about it quite like this, atoms actually move around more slowly than electrons. The reason being is that they are more massive. This means, although it sounds totally crazy, it's not impossible for our technology to measure the changes in positional energy of atoms as they track around inside molecules. However, in order to do this, you would effectively need to take pictures of the events that are happening around about once every femtosecond. A femtosecond being 1 × 10 to the minus 15 seconds. So pretty quickly then. If you try to use these incredibly short femtosecond-ish pulses of laser radiation to see what's happening with electrons inside the atoms, you're going to be disappointed. Your results would be all blurry again, just like the bird's wings earlier. If you want to study the position and energy of electrons more accurately, you need to be taking photos, in inverted commas, in the order of 1 × 10 to the minus 18 seconds. This is known as the attosecond, and here is the nub of the problem. If 10 to the minus 15 seconds is a sort of theoretical limit for lasers, and we need 1 × 10 to the minus 18 seconds to look at position or energy of electrons, then some new techniques are needed. And this is where the work of our Nobel laureates comes into focus. How are these extremely short bursts of radiation created? In essence, it comes down to the superposition of waves, something you probably know about. You can see what happens here when 2 waves of almost identical frequency are added together to give the red trace at the top. In this second example, we've added in a 3rd wave, the yellow one, which again is similar to the first 2. You can see now that the red pulse that's created by the superposition is shorter in length. The trick then to creating shorter pulses is to add more and more waves together with shorter and shorter wavelengths. When laser light is shone into a Nobel gas, ultraviolet photons can be emitted. You may remember the harmonics that are created when a string on, say, a guitar or a violin is plucked. These harmonics, also called overtones, have clearly defined relationships to each other. It turns out that the previously spoken of ultraviolet photons that are emitted from the Nobel gas come out with a series of clearly defined overtones which are directly related to the wavelength of the original laser. As you might expect, the photons from the ultraviolet gas will superpose with each other. This means when you add them together with the original laser pulse, you can create very short pulses of laser light. The length of these pulses can be anywhere in the hundreds of attoseconds range, and this is enough to begin to probe down into the very fast movements that we were talking about earlier in the video. Now, it's taken me just a few minutes to explain some of the processes behind, but as you can imagine, years of work have gone in by the Nobel laureates to get this far. It's an amazingly exciting achievement to think that we can now begin to investigate the movement and position and energy of electrons in specific times and watch what's happening deep down there. Very exciting stuff. Doubtless there will be many applications for these attosecond pulses, many of which haven't even been thought about yet, but here's just a couple. It will be possible to watch what happens as electrons are tugged away from their surrounding environment using these pulses to accurately see just what is happening. Another example would be to fire these attosecond pulses into, say, molecules, causing those molecules to emit telltale signatures, giving us a description of what is going on with those molecules, or indeed what actual molecules they in fact are.